460 billion tons of plastic were consumed in the past year, and it's a growing trend. Ladies and gentlemen, in the next 10-ish minutes we will discuss on how we can make plastic a bit less harmful and a bit more fantastic. Let's start our journey by talking plastic. Being one of the most popular materials in the past year, plastic is literally everywhere. But we've all seen the horrifying pictures of the plastic island, of sea turtles eating plastic. So, if it's everywhere, causing that much damage, why we are not just recycling everything? Well, because only half of the plastic can even be recycled. Some plastic are irrecyclable by nature. Adhesives or glues, for example, are made of such type of plastic. Some other plastic-based products are made of more than one type of plastic, like in the case of food packaging, making the recycling just not practical because of separation problems or high energy consumption. But what about the other half of plastic, the one that we are, hopefully, do throw into the orange trash bins? Well, this is also problematic. Recycling is a very harsh process, causing degradation in the plastic properties. So, if, for example, you start with a Keter plastic chair made of polypropylene, after recycling, you find yourself with a fruit basket, which is very important. We are all using it, but it's not a Keter plastic chair. So, is it really recycling? Well, debatable. But if it's everywhere, causing damage to the environment, why we are still using plastic? Well, first of all, because plastic is both light and strong. And if you want to make your product lighter, still maintaining its strength, you need to change it into plastic. That's why, in order to reduce fuel consumption, which is the main factor for pollution in the automotive and aerospace industries, the new airplanes are made of more than 70% plastic-based materials. Second, plastic is relatively cheap to produce, which is really important for mass production. Plastic also tends to be highly resistant into various conditions, and you can manufacture it using various processing techniques. One such technique is 3D printing. Being very popular in the past years, 3D printing is basically 2D printing just layer by layer until the 3D structure is formed. Now, there are several printing methods. We will be focusing on two of them. One, direct ink writing, as you can see here, or it is also relevant to fused deposition modeling, FDM, which some of you, I guess, are familiar with. It's basically the deposition of high viscous or paste-like materials layer by layer until the structure is formed. Another method is digital light processing, which using liquid-like materials that solidify under irradiation, like happens in nail polish. It's actually pretty much the same materials. So what if we could have plastic that maintain its properties after recycling? Well, this is my goal of research, to develop a new type of plastic that maintaining its properties and can even be 3D printed. But how do we develop this type of new plastic? By harvesting the properties of a special type of chemical reaction known as cycloaddition. That's okay. I know that not all of you are chemists. We will go through it together. Don't worry for this frightening reaction. The main idea is that you start with a liquid material that solidifies under radiation, usually UV light, and by irradiate it with shorter, much more higher energy but more harmful UV light, you can dissociate it back into the original materials. Sounds very promising, but two challenges for using this reaction. First, it tends to be a really slow reaction, like hours to days, which is of course not practical for application. Second, the use of harmful UV light. The answer is to develop a new type of catalyst that first accelerates the reaction and shifts the wavelength into the visible light, much less harmful. And that's what we did in our research. We developed a new type of catalyst that, based on a tin as a core metal, you can see on the right for your chemist in the crowd, the chemical structure of the catalyst, and we compared it to other catalysts exist in the literature. You can see on the y-axis how much the material has solidified and for how long we have irradiated on the x-axis. You can see that our catalyst is more than twice efficient than other catalysts exist. Now that we do have a catalyst and we can use the promising reaction we have talked about, we can try to print our material. And we did it not once, not twice, but 11 times, obtaining the same structure, the same resolution, again and again and again. But that means we've recycled it. But of course, we didn't want to use harmful UV light. So how did we recycle the material? By using something that you all have in your house, in your kitchen. Microwave oven. Yes, exactly like the one you have in your home. We found out that microwave irradiation causing vibration in the chemical structure dissociate and destabilize the material until it dissociates it back into the original material after just 10 minutes in the microwave. And you can, after these 10 minutes, print it again and again and again. We have just said in the beginning of the presentation that one problem with recycling is the loss of the properties. So of course we have checked this part and we found out that you can see the first cycle of printing, which is before recycling, and after 11 times that the mechanical properties remain the same. We don't have time to dive into it, but of course we've also analyzed the chemical structure and the thermal properties, etc. And we found out it remained without any damage. You can see it in the paper we have published about it. So we have successfully recycled the plastic. We print it, use it direct ink writing, but of course it's not everything perfect. We're still facing some challenges. We want to expand the use of the material to other printing methods, like DLP we've discussed that required low viscosity materials. So we've tried to reduce the viscosity, but found that we also increased the reaction rate. So it's still a balance we are facing. I don't have an answer for this just yet. Luckily me, I still have time until I finish my PhD, so I hope I will find a solution until then. But if any of you have any suggestion, please just let me know. So let's conclude everything. Plastic is problematic, but really necessary in our daily life. The answer may be lay in developing a new type of plastic that maintains its properties after recycling. And remember, microwave is not just good for your food, but may also be part of the future of plastic. Thank you.